Good morning. I hope you all are having a good day. We're going to start talking about chapter 12, which is the Kinetics chapter. If you took the exam yesterday, or when you take it today, or tomorrow, I am still on target for returning them on Friday. So Friday, towards the end of lecture, we'll do that, at least as of right now. But in the meantime, I'd like to talk about how chemists can fight the fact that we're lazy. And I've babbled a lot of times about chemists are lazy, always trying to do things the quickest way. And lazy sometimes means just a way to save time, all right, because you have other things to do. Kinetics is actually a field of science that studies the effect of time and how fast things go and how slow things go, why some things make a reaction go faster and some things make a reaction go slower. In this lower right-hand corner, I've got a little animation playing that shows how important this can be. So there's like a piece of paper, some iron nails, and a piece of diamond, all right? And if you just wait not too long and stuff, in theory the paper would be the easiest to combust, to get rid of. And if you put a light to it, it goes really fast. If you leave your iron nails out in the water or out in the rain or something like that, they do begin to rust. That's a slower process though, but it's something that we could observe on our time, on our human lifetime. On the other hand, diamond is actually something that's going to break down, all right? After many, many, many thousands upon thousands of years, the diamonds will turn into graphite. But you shouldn't go and sell your diamonds or anything because diamonds are decomposing so slowly, all right? So if you have any diamonds around and stuff, you shouldn't feel like you should have to go sell them. On our lifetime, the decomposition is slow. But I bring this up because all three of these things are things that are going to break down. All right, given enough time, they're all going to go away. And the question might become, well, why is this one so fast and why is this one so slow? And these are the things that kinetics will address and talk about. Another thing that I think is really fascinating that you may have heard of before is something called the Shroud of Turin. Now, this is kind of getting a little closer to sociology, history, and stuff. However, in the early 1900s, there was this place in Italy, Turin, and they claimed to have the Shroud of Jesus, all right? So this was supposedly the cloth that was put over Jesus's body when he was dead. And it's been kept in this church for a long time. Then in the early 1900s, a scientist took some photographs and they did some inverse of color. So like black became white and white became black. And you can see this kind of face that appeared. And the assumption is that this face was once on this body. Maybe this is Jesus Christ, all right? Well, here comes the scientist. And so what scientists did is using kinetics, the things we're going to talk about in this chapter, they analyzed the cloth itself. They took a little sample of it and saw. And according to the kinetics at the time, the Shroud of Turin was not 2,000-ish years old, which would be the time of Jesus. It was more about 500 years old. And so there's a lot of theories then that maybe there was this knight who was supposedly historically kind of a troublemaker, and maybe he brought this back and said, oh, this was what Jesus is, and he got it from the Middle East and stuff like that, when actually it was just some local boko guy that they had put the body over. So anyway, then some Christians came back and said, oh no, the kinetics was only looking at a certain part of the shroud, and if you look at the actual middle part of the shroud, it shows it's 2,000 years old and stuff. So I don't know what the answer is, and I encourage you to explore this on your own and come to your own conclusions. But what I am excited to share with you is that now you won't just be going from the gut. It won't be a faith-based decision. I want you to make science-based decisions and decide for yourself. Do you think it's legit? Do you think it's not? Is this Jesus? Is this somebody else? Something for you to decide. But you will have the skills now to make these kind of decisions. So, I want to kind of review here before we start talking about time, about the importance of thermodynamics. And in chemistry, as well as the physical sciences, thermodynamics is really the study more or less of the energies that happen in different reactions. Energy is the currency of chemistry, I've said before. Thermodynamics is really good about telling if a reaction is going to occur or if it's not going to occur. And that's really powerful, all right? So all of those little animation things I had in the lower right corner earlier, those are all reactions which are going to break down. But thermodynamics doesn't tell anything about how fast the reaction is going to break down. So you might have a reaction which is definitely going to go to products, but if it takes 100 million years, does it really matter in terms of our timeline? Good question. So thermodynamics doesn't say anything about the length of time required for reactants to go to products. So this field right now, which is called kinetics, it's the study of how fast reactions go. And a reaction rate is literally that. It's how fast a reaction is going to take, Gesundheit, to go from reactants to products. We can best understand these speeds of reaction, the rates, based on something called the mechanism. And the mechanism is just as important as anything else. I want to demonstrate here the importance of the mechanism, all right? So, oh, Kelsey, over there. Haven't seen you for a long time. So I decided to walk over here, and I said, hey, Kelsey, what's going on? Really glad you're here. Easy, simple, didn't have to go crazy or anything like that. That's the best way, probably, for me to get from where I was just standing to Kelsey. But all thermodynamics does is look at me before and me shaking Kelsey's hand. It doesn't say anything about the path I took. So obviously, lazy chemist me, I go in the easiest way, I walk around, no problem. I didn't have to do that. I can get up on the table and pizza me, hey, what's going on? Good to see you too, Caleb, right on. So I can walk over here, hey, what's going on right there? And I can shake Kelsey's hand this way too. Here. Notice that before and after is the same both ways, but the mechanism, going over the table, saying hi to Caleb, that wasn't part of the first one, all right? So mechanisms in chemistry are super important. Obviously, me getting up here on the desk was a little bit more time intensive, but a really good showstopper, so that's why I did it. It was a lot easier for me to go around the table, and this is what we're going to talk about in this section.
And another path will be through a wormhole.
Dimitri is looking at some really cool kind of astrochemistry things. That was a cool comment. If you find one, you let me know. Deep space now. All right, Prof. Back on Star Trek references. Yeah?
Couldn't you also, in theory, just kind of walk out the door, take a run, and then come back?
You bet. That's right. I could have walked out the door there back by Christian, and I could have ran around the block by the testing center, came in this door. Absolutely, man. That would be the same before and after, but obviously a different path.
So are we looking for the least amount of energy used, or the...
Oh, we're going to talk about all that coming up, so you hang on. Other questions? So let's think about some generic reaction of red A going to blue B. All right, and let's talk about it. So we're starting with a mole of pure red A. And after a while, the red is going to the blue, which has to do with the energy, Dimitri. We'll talk about your stuff coming up too. Red going to blue. And you can see that after 20 seconds, maybe you've got about half and half, all right, roughly after that. And then after 40 seconds have elapsed, now you're down to just 0.3 moles of A and 0.7 moles of B. So you're seeing here the dependence on time. Reactions don't usually occur like instantaneously, and when there's 10 to the 23rd of them running around, it will take longer times and less times. So we need a way as chemists to describe the speed or the rate of the reaction. And if we were driving from here to Hood River, all right, we could totally describe our speed in miles per hour or kilometers per hour, something like that. And the car would go so fast and stuff. We need something like that, though, for chemistry, all right? We need some way to talk about how fast A is being used up, and sometimes it will be helpful to think about how fast B is appearing. So one thing we run into when you start thinking about speeds in chemistry is that you can think about the speed of the reactant as it is being used up, And you can also think about the speed of the product as it appears. So speed in chemistry is a little bit different than like miles per hour in a vehicle, but the idea is comparable. Reactants are going to be decreasing over time, and products should be appearing with time. Now, speeds are always change in something over change in time. So if you have a reactant, the final reactant will be less than the initial reactant. So if you're doing a change in the concentration, reactants are always going to have a negative sign because they're being used up. Final reactant will be less than initial reactant, so final minus initial will be negative. On the other hand, products are always increasing, they're appearing, so the final amount of product should be greater than the initial amount of product. So what chemists have come up with is a system that looks like this. It's a way to describe the speed of a reaction from either a reactant or a product perspective. And this is really pretty cool. So again, in chemistry, sometimes it's nice to think about how fast the reactants are going away. And it's also nice to think about how fast the products are appearing. And also though, because of the difference in stoichiometries, you're going to have twice as much NO2 appearing as the N2O4 is disappearing. So when it all comes down to it, the speed of a reaction, if it's a reactant, you put a negative sign in front of it, and if it's a product, you put a positive sign in front of it. The stoichiometry, it's 1 over that number. And what this results in is we have a way to describe the speed of a reaction from either the reactant or the product. So notice here that N2O4 is a reactant. We put a negative sign in front of it. And there's only a 1 right there, so 1 over 1, we just ignore it. On the other hand, the products here, they have a positive sign because those are appearing, and we're going to go 1 over 2 to compensate. If we didn't have this part, then the NO2 would be appearing twice as fast as the N2O4 disappeared. So the punchline is that chemists have figured out a way to describe the speed for either the reactant or the product perspective. And that's really cool in my world, because sometimes reactant will be easier and sometimes product will be easier. But what you have to do, put a negative sign in front of the reactants, put a positive sign in front of the products, and you go 1 over the stoichiometry. Now don't be fooled or misled by these little deltas. These are just final minus initial. So the final NO2 minus the initial NO2 would be this part. This is delta time, so it would be the final time minus the initial time. And the same thing over here. And if you do that, you can describe a reaction from either the reactant or the product, and it will apply overall to the whole thing. Let's look at how this works out. This is a reaction where N2 and O2 are combined to make nitrogen monoxide. So again, N2 and O2 are reactants, and NO is a product. And also notice that stoichiometry of 2 right there, all right? This is an actual graph of this reaction, all right? And the blue line are N2 and O2, and they both started about right here at 17 or 18. This is called a micromole, don't worry about that. And if they start at the same concentration, they will be used up at the same value, but the NO is appearing twice as fast. That's because of this 2 thing right here. So if we wanted to describe the speed of this reaction, this is kind of the way that we're going to think about it. You can think about it from either reactant, N2 and O2, or product. You put a negative in front of the reactants, that products are positive, and you always go 1 over the stoichiometry. So notice here, delta T is final time minus initial time. For N2, it would be the final nitrogen concentration minus the initial concentration. It's kind of cool how people have figured this out. So again, if you have a reaction, the speed of the reaction can be defined from either the reactant perspective or the product perspective. If you put negatives in front of the reactants and 1 over the stoichiometry, good to go. Here's an example of what this is. This is just an example of having some blue dye, and bleach is really good about taking the colors out of things, including the blue dye from bleach. So as you add the bleach to the blue dye, you can think about this y-axis as the concentration of the blue dye. And as the bleach begins to do its magic, the amount of blue is going down, and that's what this curve here is representing. So let's say that we wanted to find the speed of this, how the dye is being used up. It's a negative delta dye, change in the dye concentration over the change in time. So if we did 1 minute from 0 minutes, that's where the delta t, the delta time comes in. And you can probably see that at 1 minute, the concentration, let's see, it's about, well, they use this value, I guess, right here. The final concentration is about 2, and the initial concentration was 3.4. So this is like final concentration minus initial concentration. This number right here is like the speed of a reaction. And it's not quite as cool sounding as like a miles per hour. It's usually in molarity per unit time. So in this case, it's moles per liter per minute. That's how fast the bleach is being used up at this point.
Pouring bleach into a beaker of water and blue food dye converts the dye molecules into a colorless form. The timer indicates the progression of the reaction. If we plot the concentration of dye molecules at various times over the course of the reaction, we can determine the rate of the reaction.
So rates are nothing more than how much of a chemical is being used up for time. So just like a speed of a car is how many miles are driven per hour or whatever, in chemistry it's usually about how many moles or moles per liter are used up per unit time. In this case it's per minute, it could be per hour, it could be per second, stuff like that. There's several types of rates. We're only going to use average rates in our class. If you've taken calculus and stuff, there's lots of different ways with derivatives to do this stuff. But in this class, we're not going to do any kind of derivative things. So we're just going to look at kind of the average rate overall. So what you can do, for example, is you can go like the speed per time. So in 15 minutes, 0.12 moles per liter have been used up. That would be the speed per minute, all right? You can also do instantaneous times. The slope of the curve at the point is basically a way to tell that. That's more than we need to do right now. But for right now, just realize that all of these speeds, these are speeds of the reactions. And some reactions are really fast and some reactions are really slow. And the speed literally is going to be how many moles per liter are used up per minute or per second.
So if we ever do something like lab related, how many rates of reaction do you want us to plot in order to find the average?
Cool. It's going to be much more obvious what we're going to do in lab. And in the lab that you will do tomorrow, and some people did yesterday and some of you will do today, the rate of the reaction is really just the iodine concentration divided by time elapsed. And you'll see where that comes in more. This is an area you can get into a lot more detail. All right, we're just kind of doing a quick overview. I think this will maybe help. This is a graph of some random reaction, all right? And it's a reactant, and we know it's a reactant because this curve is decreasing. Reactants are always going down. They're decreasing over time. So let's say that we wanted to know what the speed or the rate was for the first 2 minutes, all right? So we go down here to 2, to that point, and here is 0. So it's change in the concentration divided by change in time, all right? So the concentration right here would be 1.7-ish, and the concentration up here maybe 3.4. So that would be the top part. That would be the change in the concentration. On the bottom part, you would have the change in time. And for 2 minutes, it would be 2 minus 0. So if you put this together, here's the 1.7 minus 3.4. Delta T would be 2 minus 0. Because it's a reactant, I'm going to put a negative sign in front of it. If it's a reactant, you put a negative sign. If it's a product, you put a positive sign. This reaction is 0.85 molarity per minute. So every minute then, this thing is going down by 0.85 moles per liter.
What makes the graph a reactant? Is it due to the sort of concave ups, down slope?
No, easier. What's happening in a reaction to the reactant, assuming it's happening?
It's decreasing.
Decreasing, yeah, that's all it is.
Oh,
So it is, you can think about it in concave and stuff like that, but really it's simpler. It's just reactants should be decreasing and products should be increasing. Okay, good. Other questions? All right. So what we're going to do is talk about things that affect the speed of the reaction, and there's actually quite a few. Concentration of reactants is a big part, all right? Some reactants are really, they will affect the speed a lot, and some won't affect it at all. And this is one of the things we'll be exploring in lab. Surface area is actually important too. If you have a system with like a couple of solids, the surface area where the chemicals are allowed to react will slow reactions down. Temperature, definitely important. Kind of cold and dreary out today and stuff, not as exciting as warm days. So temperature is a factor. And then finally, a catalyst is another thing that will affect it. We've seen some examples of catalysts in the past with MnO2. We're using a catalyst in lab this week as well.
In the test tubes is hydrochloric acid. On the left is a 0.3 molar solution, and on the right is a 6 molar solution. If we place a strip of magnesium metal in the 0.3 molar solution, the metal begins to react slowly. If we place a similar magnesium strip in the 6 molar solution, the reaction is much more vigorous. Within moments, the reaction is complete. Meanwhile, most of the magnesium in the 0.3 molar solution is still in solid form.
So you can see here how the effect of concentration is very important for a reaction. The left-hand side, 0.3 molar HCl, and it is reacting. All right, those bubbles that are forming are the hydrogen gas, all that kind of stuff. But man, you put it in the 6 molar solution and whoa, talk about a lot more exciting. There's no magnesium left. It's all gone. It's all been turned into hydrogen gas. So we're seeing here the effect that an additional HCl, kick in the pants, if you will, does a good job relative to the more mellow HCl. So the concentration is going to be a big part. We're going to look at concentration a lot in the lab this week as you have very different concentrations.
On the plate is a pile of lycopodium powder. If we aim a flame at it, not much happens. If, however, we take some of the lycopodium and then spray it into a flame, the combustion reaction is explosive. The more surface area of the lycopodium particles that is exposed to oxygen, the faster the reaction.
Lycopodium powder is a type of a mushroom that they ground up, and I don't know more than that, but anyway, if you put a flame directly on a pile of lycopodium, like nothing happens, and you're like, oh boy. However, if you spray the lycopodium powder through the flame, then you get these really dramatic effects, and sometimes in magic tricks, they'll have like little lycopodiums that they'll throw into flames, and and it looks like you're a magician or something. So anyway, lycopodium powder is something you can get at natural food stores. It's kind of an interesting thing. However, what we're seeing here beyond just cheesy magic tricks is the effect of surface area, all right? If you have really fine particles of lycopodium going through the flame, they catch on fire easily. In its concentrated form, like only the outside was having any reaction, and it was very slow. So the surface area can be a factor when it comes to reaction.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
Catalyst is just something that makes your reaction go faster. And if you took Chem 221, the percent KClO3 lab, we also added MnO2, and it made the decomposition that much faster. The lab we're doing this week, the acid, as it turns out, is actually a catalyst as well. A catalyst will make the reactions happen a lot faster. So this was hydrogen peroxide decomposing. In theory, you could recollect the catalyst at the end and use it again. So like in this case, it would be easy. You would just evaporate off the water, you'd have the MnO2, and you could place it in more hydrogen peroxide to make it go. MnO2 is a relatively cheap chemical, so we don't usually do that. On the other hand, there are some catalysts with like rhodium and platinum metals, really expensive metals, and they definitely will collect those at the end to reuse them, make them go over and over. So catalyst is not used up in the reaction, but it does make it occur faster, and we'll talk about that later, what's going on.
If we pour equal amounts of hot and room temperature bleach into separate beakers of colored water, we see that the hot bleach on the left destroys dye molecules more rapidly than the room temperature bleach on the right.
So again, here's a temperature effect. The warm temperature makes the reaction occur a lot faster than the cold temperature will. It will still react at the colder temperature, it just takes longer. So this is a lot of times when chemists are lazy, if we just change the temperature, I think it would go faster. But anyway, you're seeing here that something's happening that affects the speed of the reaction, and this is what we'll talk about here too. So, if you're going to start thinking about reactions and how fast they go, there's really two things you need to do, all right? You need to first of all figure out the factors that make it go faster and slower, which is the reaction rate. And also though, to really see why there's effects of concentration, we need to postulate a mechanism. So me walking over to Kelsey earlier, all right, you might think normally I would go the lowest energy, but there was nothing to keep me from going over the desk earlier. And as Caleb pointed out, I could actually walk outside, walk around the building, and come in and see Kelsey that way too. So knowing the mechanism, the route that reactants take to get to products will give lots of hints as to why some reactions are fast and some reactions are slow. So first, what we're going to do, this first section, is think about ways to figure out what makes a reaction faster and what makes a reaction slower. And then in the second part, when we talk about mechanisms, we'll try to understand why some reactions are faster and why they're slower. So in talking about then the rate, all right, here's an example of a compound called cisplatin. And cisplatin is an anti-cancer drug. But anyway, another reaction it does, which isn't as exciting as anti-cancer, is it does react with water. And one of the chlorines are kicked out, and the water tends to bind then to the platinum. So this is just like a type of substitution. By the way, notice that cis here, it's another form, another interpretation, if you will, of cis. We've seen cis around double bonds, where the two similar pieces were on opposite carbons but same sides. Sometimes with metals, cis will mean like at 90 degrees like that, and you could have in theory then like a trans cis, which would be CLs across from each other. We'll see this later, but anyway, For right now, people have studied this reaction a lot. Anything to do with cancer usually has a lot of interest for obvious reasons. So how fast this platinum compound will change depends on the amount you start with, which is like the moles per liter of cisplatinum, and the amount of time you're willing to wait for it to happen. So it's like a type of a concentration divided by the time elapsed. So let's say that we had a speed that someone had studied 4.3 times 10 to the minus 6 molar per second. The little second minus 1 there means it's in the bottom part. So you could write this as m divided by s, moles per liter per second. But on the other hand, if you don't want to use denominators, this means that it's in the denominator. So this means that's the speed moles per liter per second. The question is here, we can actually use this information to find the approximate time that the cisplatin is going to react. So let's say that we had 0.00250 molar of cisplatinum, and we wanted to know how long we'd have to wait. Well, if you look at the units, here's moles per liter per second, and here's moles per liter. So if we can cancel those moles per liter and have just time, that's going to be a cool way to approximate how long this is going to take. So in this problem, lazy chemists want to know how long it's going to take. All right, moles per liter divided by moles per liter per second. The second on the bottom will come up to will be a regular second on the top. Mathematically throw this in your calculator. This one should take approximately 581 seconds. I say it's approximate because this is an average rate. It's not necessarily the ultimate rate like Dimitri asked about earlier. However, you can get a rough guesstimate as to how long these reactions are going to take if you know the speed or the rate and you know the concentration you're starting with. Hint, hint, hint. Post-lab questions, Kinetics 1 lab. Anyway, so the rate of the reaction does depend on the concentration of the chemical that you start with. More starting chemical, takes more time to make it happen. So a rate law is something that scientists are going to figure out. And for this cisplatin reaction, the rate law equals K, which is called the rate constant, times the concentration of this cisplatinum. So this part right here is kind of cool for chemists because the rate is that moles per liter per second. This is how fast the reaction's going. And if we know the concentration and we know the rate constant, you can figure these kind of things out. So this K, this rate constant, is a pretty cool thing for chemists to know. And the Kinetics Part 1 lab is basically trying to find the rate constant K for the reaction we're going to study. So I like to think about the rate constant K as being like a holy grail of kinetics. If you can find the K, then you can find the rate if you know the initial concentration, stuff like that. K's depend on temperature, so you change the temperature and K no longer applies. But if you do have K and you know all of these parts, this can be pretty handy. So the rate constant K is just a number. It's a positive number. The positive number reflects really how fast this reaction is going to go. And we're going to talk about ways to find K here in just a second.
Will we be using regressions to find these type of numbers?
No. There's in the stuff we're going to do, Dimitri, we will use some regressions in the second part, the mechanisms part, but not this part here. Good. So, when people have a new reaction and they want to find the rate constant K, they have to take into account the effects of the different reactants and stuff on the speed. So let's say we have a generic reaction where big A and big B are reacting to make compound X, and we have some kind of catalyst C. Catalysts and the reactants are the things that are going to affect how fast the reaction goes. So you can write in a generic form, rate equals K, that magic rate constant, times the concentration of A to the M power, B to the N power, and C to the P power. And these little M, N's, and P's are called reaction orders. And that's probably the most important thing to find in a reaction outside of the rate constant itself. And reaction orders kind of indicate the importance of those chemicals in regarding the speed. Now, in Chem 222 and Chem 223, the only values of reaction order are going to be 0, 1, and 2. And those are most of the things. Outside of Chem 223, then most of the time you're only going to have zeros, ones, and twos as well. Sometimes you'll have some other weird kind of combinations, but in our classes, the only values for those rate orders are going to be 0, 1, and 2. You have to find these through experiment, all right? The only way to find these 0, 1, and 2 numbers is by actually going through and doing experiments. The lab this week is basically changing the concentrations in order to find what the 0, 1, and 2 values are for the acetone, the HCl, and the iodine. But again, remember, your answers are always going to be this. So if you get like a calculated value of minus 0.25, round up to the nearest order, minus 0.25 would be 0. And if you had 1.15, you would round to 1, etc., etc. So, sometimes people will talk about the overall order. We won't do that a lot, but if you do see it, you just add all the individual numbers up, and I'll talk about that a little bit later. Sometimes in literature they'll do that, but anyway. So let's talk about what these 0, 1s, and 2s mean. If you have something that m equals 1, all right, that means that if it's for A, there's a dependence of A on the speed. So speed, remember, is rate. So let's say you had a first order A, and so that's what the 1 means. And you doubled A, so you went from 1 mole per liter to 2 moles per liter. To figure out how the speed changes, that's where these orders come in. So if you double something, it's like 2 to the first power. And what is mathematically 2 to the first power? 2, that's right. So if you double A, your speed is going to go up by 2. And if you triple A, 3 to the first power, your speed or rate is going to go up by 3. So this is by far the most common kind of rate piece. First order things. You double the concentration, your speed goes up by 2. If you cut the concentration by 2, make it 1/2 of what it was, your speed goes 1/2 as fast too. It's going to slow down. So first order means you double something, the speed goes up by 2, etc., etc. However, there's also m equals 2. If you have an m equals 2 reactant, then you're going to put a 2 right there. So a second order reactant means in the rate law, this thing right here, you're going to have a 2 by the reactant. If you were to double A, and A is a second order reactant, the effect on the speed or rate would be 2 squared. So if we double A, what does that mean the speed would be?
Exponential.
4, yeah. Yeah, it would be double, it would use the second power. That's right, that's right. So the speed would go up by 4. It would be like 2 squared. What would be the effect of the speed if we tripled a second order reactant? 9. 3 squared. Whatever number you change the concentration, you square it, all right? So 4 squared, 16, etc., etc. If you have a second order reactant, the effect on the speed is incredible. Like you'll accidentally have an extra milliliter and all of a sudden the reaction is like done. It's amazing how fast these things will happen. There aren't a lot of second order reactants, but when you see one, the effect on the speed is quite dramatic. A lot of reactions though are considered zero order reactants, all right? And zero order reactants have a little 0 right there. What is any number to the 0 power? 1, all right? So if you would double A and it's 0 order, do you think there'd be any effect on the speed?
No.
No. 0 order reactants don't affect the speed at all right? because they have a 0 right there. You can double them, triple them, halve them, anything like that, and you're not going to see any effect on the speed
In
whatsoever.
other words, they're spectators of the reaction.
Well, they don't affect the speed. And Dimitri brings up a good question here, man. We're talking about things that make the speed go faster and slower, all right? And so if you have a 0 order, it won't affect the speed. But they still are part of the chemistry, all right? They're in there because they're a reactant or something like that. Other questions? Good. Faith, do you have any questions? Good. Other questions? All right. So let's look at a practical example of how you would figure out if something is 0, first, or second order. Remember, those are the only possibilities. This is a question involving something called ethanol, all right, or it has different names. And we want to figure out what the rate order is for ethanol. So remember that anytime you have a rate law, the speed rate is going to equal K times, in this case, the ethanol, which is what we're looking at, and then to the x power. And our goal here is to find out what the x is. And x is going to be 0, 1, or 2 only. So what you need to do is you need to vary the concentration of the chemical you're looking for. And there's usually some way to find this number. This is the speed. It's how fast the chemical is being used up per second. So in this first one, at 0.10 moles per liter ethanol, the rate 0.020 molar per second. Whoopie-doo. Doubling ethanol, 0.10 to 0.20, notice the effect on the speed, all right? 0.020 to 0.081. Approximately, what is the change in the speed over here as you go from 1 to 2? Yeah, about 4 times. 0.02 times 4 would be 0.08. So this is like having the speed go up by 4 times. What did we do to the concentration of the ethanol?
We doubled it.
Doubled it. So really, at this point, it's like 2 to the x. We're doubling the ethanol, makes a change in the rate of 4. 2 to the x equals 4. X is only going to be 0, 1, and 2. What do you think x is going to be just based on these 2 points?
2.
2. Well done. So because we doubled the ethanol and the speed went up by 4, you can think about it as 2 to the x equals 4. And 4 is this divided by this, and 2 is this divided by this. And we don't know x, but literally with only 2 values, you can do it. What do you think the value would be, what would be the rate change if x was a first order, like if it was 0.1 to 0.2 and x was 1? What do you think would be the approximate rate?
0.040.
0.040, well done. So if you doubled 0.020 to get 0.040, that would be 2 to the first power equals a change in 2. So if this would have been about 0.04, that would have been a reasonable thing. If x was a 0 order reactant and you doubled the rate, what do you think the approximate rate would be of the second one?
0.020.
Nice. If you have a 0 order reactant, there should be no change in this number over here. And so if this was a 0 and this was 0.020, you'd think that this would be about 0.020. So without even going through any more things, you can kind of hopefully begin to see this is how scientists think about these speeds. If you double the rate, you double the concentration, you look for the change in the rate, and you only have 3 possibilities. Alicia, and then...
Will the x value that we're trying to find always be the same for that same equation no matter how many times we do it?
Yes, as long as you don't change, like, ethanol does more than this reaction, okay? But as long as you're looking at just this reaction and you don't change the temperature, this will apply all the time. Right on. Alvin.
I just want to confirm that, so we find x by taking the log of difference.
Yeah, on the next page, I'll have a more formal way to do it, all right? This way I'm doing it right now, and I call it kind of a hand-waving way, and some people like it, but if you don't, I'll show you the logarithm way here in just a second.
So it's like 2 to the what power equals 4, basically?
Yep, that's exactly it. I'll talk about what Alvin's doing here in a little bit. Yeah, Papa.
That's what we were asking, is it gonna be like, I don't know if you got there yet, deriving like in math, calculus, dropping the power kind of thing?
Yeah, you're seeing the fancier way of doing it. I will show the non-calculus way of doing it, but honestly, you can use all those techniques, and that's pretty cool. Absolutely. Other questions? Good. Remember that in this class, you don't have to have calculus or anything like that. So there's always ways to get around it. Maybe a little cheesier, all right, but still they'll work really good. Okay, so in this example, we changed, we did more than just 2 trials. We went from point 1 to point 2 to point 3 to point 4. And over here are the different parts. Now notice that you could also do my hand-waving version of this by looking at point 2 to point 4, because this is a doubling as well. So if you take 0.318 divided by 0.081, it's about 4. So doubling the concentration is about a change of 4. That's another way to see. But I know that feels weird, so let me show you an alternative way to do this. All right? You can apply the rates. You take the difference in the rates, which in 2 to 1 is this number right here. And you take then rate equals K times the concentration to the X, and we're trying to find that little X right now. So this is like fun with math. The difference in these numbers is 4.1. The K over K will cancel. And this part right here, this is one thing that people like in logarithms. 0.2 to the x divided by 0.1 to the x is like parentheses 0.2 divided by 0.1 to the x, and that's where the 2 to the x comes from. So 4.1 equals 2 to the x. X can only be 0, 1, and 2, all right? So in this case, x has to be 2. 2 squared is about 4.1. This is science, this is experiments. It won't be probably exactly 4, but it's pretty close. Now, this reaction is considered second order. Now, Alvin asked earlier, though, about the logarithm way, which is totally... Oh, I'm going to show this first. Oh, hold on. I want to come... Oh, fascist... Okay, sorry, I'm obviously having a brain spaz here, so yeah. Well, anyway, oh, this is embarrassing instructor moments 101. At this point, you could also, let's talk about it more officially. You could go log 4.1 equals log 2 to the x, and log 2 to the x is x log 2. Let me write that out. I thought I had notes on this. I'm obviously having a spaz. So you can also go log of both sides, and you can use base 10 logs or regular logs. If you do the log of both sides, 2.0 to the x is what you can do here. And this is probably the best way. Now, chemists used to use logarithms all the time, and this is why. This thing can be rewritten as x log 2.0. And if you want to get the x by itself, then you can just divide both sides by log 2.0. These parts over here cancel out. X is literally just log 4.1 divided by 2.0, and it does come out to be about 2. So this is an alternate way, and Alvin, I should have done a better job explaining this. Yeah.
So when we did the linear regression lab, and the last problem asked us about the second order, that's what this is talking about.
Yes, that's what we're getting into, man. That's right, and we'll talk about that coming up. Well done. Dimitri, remember from our linear regression part, there was a first order, second order. Oh, yeah. Okay. So here's a reaction. NO plus hydrogen gas makes N2 and 2 waters. The reaction is second order in NO and third order overall. And if you want to find the rate law then, the second order in NO means that you're going to have a 2 by the NO. Now third order overall means that if you add up all these little exponents, they're going to equal 3. So if this one is 2, you can probably figure out then that the hydrogen is going to be just 1. It's going to be first order, and 2 plus 1 means third order overall. I'm introducing this naming because once in a while you'll see this in the literature. So overall rate orders would be 2 plus 1, 3. Hydrogen is first order, NO is second order, and overall 2 plus 1, this is third order overall. Questions? Okay, we'll continue on with this part on Friday. All right, have a wonderful day. I'll see you soon.